Okay, so one of the main ideas uh, of this week is going to be the understanding of pressure as coming from the kinetic energy of all the particles. What do I mean by that? Let's look at this gas here, and you can see every one of these particles after equilibrium is going to be moving, right? So if you want to measure the pressure is just basically the force of these particles on the walls. For instance, if you look at this bottom wall or this side wall, there are particles colliding with it all the time. And then those collisions, they produce forces on this wall, and those forces are basically the pressure. So we are going to be able to write at the end of this video that the pressure is just the force divided by the area, right? It's the force on this wall divided by the area of the wall, and that is going to be equal to 1/3 of the number of particles divided by the volume times the mass of the particles times the velocity that we're going to call RMS, and we're going to define that later, squared. But this is basically the pressure basically depends on what? The number of particles. The more particles you have, the more collisions you have. It's inversely proportional to the volume. The bigger this area, then the less collisions you have and the less force. It's going to be divided by 1 over 3 because you have three coordinates, right? And there's no special direction, so this is the reason of this 1 over 3. The mass of the particles, the heavier the particles, the more forces on the wall, and the speed of the particle, right? The speed of the particle square, and this is sort of an average speed of the particles, of all the particles, and the faster they are going, then the more force on the wall. This is going to be the idea of the pressure, and we are going to try to relate here, and let's go back to the slides, and let's look at a gas. And a gas like the one I was showing in the video is basically many millions of billions of particles, and they collide. They collide with the walls every second, and there are millions of collisions with the wall. So here we have a histogram of the velocities of the particles as in a gas, right? And then you can see that about 16% of the particles have this velocity, which is about 600 meters per second. This is an N2, this is nitrogen at 20 degrees at room temperature. And then you see that most particles, this is 16, this is about 20%, this is about 20%, so this is 40%. This is another 16 and 16, so this is 30. So this is about 70% of all the particles. They have speeds between 300 and 700 meters per second for nitrogen. And you can get an average speed of that, right? You can sum all the velocities of all the particles and then divide by the number of particles, and you get an average speed. To understand this a little better, we need to introduce the idea of mean free path. A mean free path is just basically the average distance that a particle travels between collisions. For instance, we have here in this picture the trajectory of a particle. So it starts here and then move all the way here, and there's a collision here, then it moves this way, then there's another collision here, then it moves this way, then there's another collision, then it moves this way, and so on, right? And you can calculate, right? You can calculate the length of this, assume that you can calculate the length of this trajectory, right? And we are going to call that L. Then the distance between collisions, right? The distance between collisions that we call lambda, that distance between collisions is going to be what? It's going to be the length of this whole thing here divided by the number of collisions, right? The number of collisions. So that's this distance, right? And then we can prove, and this is on page 543 of the second version of your book, if you have it. And I'm not going to go through all the details here, but you can prove that this average distance here is 1, or is 1 divided by what? Divided by the density and the size of the particle, this r being the size of the particle, and some constants here. So what this basically is the r. So this is an equation for the mean free path. And remember, the mean free path is nothing else but the distance between collisions. So now, with that idea of mean free path, we can start talking about pressure, right? So before that, let's go through this question here. You have a temperature of a rigid container of oxygen. Oxygen is a diatomic molecule, is O2. Is lower from 300 degrees Celsius to 0 degrees Celsius, right? So now you can think that this means the particles are moving slower. The kinetic energy of the particles is decreasing, right? So that's what this means in this context. As a result, the mean free path of the oxygen molecules is going to increase, is unchanged, or decreases. Take a minute to answer this question. And it's going to remain unchanged. Why? Well, let's go back to the slide here. So this is the mean free path, and you can see that it only depends on the number of particles and the volume. So if you reduce the speed, and this is true for an ideal gas only, if you reduce the speed, then uh, what happens is the number of particles and the volumes are unchanged, and therefore the mean free path are not gonna is not gonna be changed.